Question 20 from the Mechanics 3 review pack. I've started off, I've just modified the diagram a little bit. I've put tension A and tension B in, and I've just stated we're going to apply Newton's second law at this situation, which is currently in equilibrium. I've taken to the right as positive, so TB minus TA equals 0. Essentially I'm going to use Hooke's law to find TB and TA, so I'm going to modify the diagram a little bit. I'm going to first of all mark on where the natural length of the strings would be attached from A and from B. Sorry, the springs, not strings in this case. And I can see that the distance between A and B is 5 metres, the sum of the lengths of the springs is 3 metres, and therefore the total extension is 2 metres. I'll therefore let one of the extensions be called E, meaning the other one must be 2 minus E. Once I've done that, then I can use Hooke's law directly using the given values, and that will lead me to finding a value for the extension E in equilibrium position. So I find out that E is equal to 1.2. Just follow the calculation and make sure you're happy with that. Okay, I'm just going to write down the final answer then. I get these two values. E is 1.2 for the 2 metre spring and E is 0.8 for the 1 metre spring. Now for the second part of the question we're going to have to prove that the particle P performs simple harmonic motion, and the way we do that is we basically just analyse the forces acting when we're in a general position. So we need a new diagram. Let's just put that down. I'm just going to pause this a minute. I've just copied the previous diagram. P, of course, whoops, P isn't there. That's just the equilibrium position now. So there's our equilibrium position, and I'll just put some information down. And what I'm actually going to do is analyse in this general position here, as shown in red, and I've said that that's a displacement of x from the equilibrium position E. And with a little bit of thought, you should now be able to see that for the 2 metre spring the total extension is 1.2 plus x, and for the 1 metre spring it will now be 0.8 minus x. Okay, so we can use Newton's second law again, and that will lead us to the following. Now I'm just going to pause it here a second. So I've got the tension in B minus the tension in A is equal to mass times the acceleration. The one thing I check at this stage is that the constant values on the left hand side are going to cancel out. Now 12 times 0.8 is 9.6, and if I do the 16 divided by 2 gives me 8, so minus 8 times 1.2 is minus 9.6. I can see that indeed they're going to cancel out. So if I carry on, I'll write it out first. I can see they've cancelled, and that will leave me with x dot dot, the second derivative of displacement, i.e. the acceleration, is equal to minus 40 times by x, and then I can compare that with the standard simple harmonic motion expression for acceleration and deduce that simple harmonic motion does occur, and furthermore w squared or omega squared will be equal to 40. Very, very standard approach to such questions. Practice a couple of times and make sure you're happy with that. Okay, let's have a look at the final part of this question, part C. So this time we're given that the initial speed of P is root 10, so that's when it was in its equilibrium position, and it must be given some kind of impulse such that its initial speed is as shown, and we've got to find the proportion of time in each complete oscillation for which P stays within 0.25 of the equilibrium position. There are several ways that I could do this. I could find an expression for the displacement, i.e. something like x equals a sine wt, and work for that. Alternatively, I could work on the associated circular motion, which is my preferred method. Regardless of which I do, I'm actually going to need the amplitude of this motion. Now, the key thing to realise for this part is the speed or the velocity at the equilibrium position is actually the maximum velocity it can have, i.e. Vmax, and we know an expression for that. So I can write down that Vmax is equal to root 10 as told, But Vmax actually is equal to WA or omega A, and that allows me to deduce that A is in fact equal to 1/2. Okay, I'm going to draw a circle down, and I'm just going to add some information on. And essentially what I'm saying when I do this approach is that as our particle moves from, let's say, this position here to this position here, so moving from right to left, an associated particle would move around where I've just highlighted in yellow, and it would take exactly the same time. So that's how long it will be when it's moving from right to left within 0.25, however long it takes for that shaded part. Of course, a little bit of thought will tell you that's not the only time, and a bit later on I'm going to have to consider what happens when it moves from left to right, which on my diagram is actually going to be somewhere down here. But we'll cross that bridge when we get to it. Very simple bit of trigonometry then leads us to the fact that this angle theta at the top is 60 degrees. So in terms of what proportion of the overall periodic time it's moving on the top shaded part, it'd be 60 over 360. Just modifying my diagram now to appreciate that I've also got to consider moving from left to right will give me that angle theta is also obviously 60. So that means that for 120 degrees worth, if you will, of the motion, it will be within the specified distances. As a proportion of the periodic time, then that would be 120 out of 360, which is 1/3 of the time. If I actually wanted to find how much time it spent within that distance, then it's just a short further calculation. So I'll just do that at the bottom. So it'd be 1/3 of the periodic time, which would simply be 1/3 times by 2 pi over root 40.